Hi, this video is going to be about informed search. That is different than the last thing we talked about, which was uninformed search. So just to review, uninformed search are search strategies that don't consider any outside information. So they only consider what is in the problem formulation. And they only consider that whenever trying to select nodes to expand to get closer to the goal. The problem with this is that it leads to high time complexity values and sometimes space complexity as well. You may recall that both DFS and BFS both have exponential time complexity, which is pretty bad for real-world problems, and they can usually lead to suboptimal paths as well. Most of the attempts that we saw to make these issues better end up sacrificing completeness, which is something that we want to hold on to if possible. And really at the root of this issue is that uninformed search strategies are just expanding too many nodes. They're not really trying to expand nodes in an intelligent way, they're just brute forcing their way through the state space, and because of that you end up expanding almost every node in the state space, which is just, usually it is way too many nodes to expand. So informed search strategies are going to use something called heuristic functions. And heuristic functions are functions that estimate how close a node is to some goal node. So given any node in the state space, it can output some number, some value that says this is how close this node is to the goal. And the idea is that including this information informs our searching algorithms to select better nodes for expansion. So every time that we need to expand a node, instead of just popping off whatever is the front or at the back of our open list, we consider all the nodes in our open list and we say, okay, which one of you is most likely the closest of these nodes to the goal? And whichever we think is the closest to the goal, that's the one that we're going to expand. And in general, when you do this, the overall result or the overall goal here is that we want to expand fewer nodes so that we can find the goal faster. One important thing to note is that heuristics are defined by the programmer or like the designer of the algorithm because they're based on domain knowledge. So it's not something you just automatically compute in your program. This is something that you come up with and then you implement yourself. So it's outside information that you know based on expert knowledge about the problem that you're trying to solve. So let's look at an example. So we're going to go over common heuristic functions for some common problems. So one problem is the 8-puzzle problem, or 8-tile puzzle, I think it's called. Anyway, we have a 3x3 board of tiles. We have 8 numbered tiles, and one of the spots is going to be blank. It's going to be without a tile. So over here in the start state, we just see some random configuration of these tiles. And our goal state is some other configuration of the tiles. And we have to go from the start state to the goal state by only moving tiles into that blank spot. So over here on the left in our start state, one of our possible actions could be moving the 2 into the blank spot, moving the 6 into the blank spot, moving the 3 there, or moving the 5 there. And then the next action would be moving a tile into whatever the new blank spot is. And we just keep repeating those actions until we end up with the same configuration as the goal state. So one of the most common heuristics for this problem is the number of misplaced tiles. So you can take any node that you can generate for this problem, compare it to the goal state, and take each one of the locations and say, is this tile in the correct spot? And compare it with the goal state. And if it is in the correct spot, then you add nothing. If it's not in the correct spot, you add 1. So I've listed here that the heuristic of the start state is equal to 8. So what does that mean? That means that 8 of the tiles are not in the position they need to be at to be in the goal state. So here, let's look at 7. So in the goal state, 7 is in the bottom middle. In the start state, it's in the top left. So that is a misplaced tile. If we go to the next one, we have 2. So 2 is in the top middle. In the goal state, 2 is in the top right. So that's a misplaced tile. Then we go to 4. We see that's also misplaced. And all of these are actually going to end up being misplaced. So the overall heuristic value of the starting state is 8. So 8 misplaced tiles. One thing to note is that the goal state is always going to have a heuristic of 0. So if we try to compare the locations of all the tiles in the goal state with themselves, none of those are going to be misplaced. So the heuristic value of the goal state is going to be equal to 0. So another common heuristic here is going to be the sum of the distances to the goal position. So this one's a little bit more involved. So what this is saying is that whenever we have a misplaced tile, count the blocks that it would take to move that tile into its goal position. So here I've listed that the starting state has a heuristic value of 18 if we use this heuristic. So we'll go up to the top here. We start at 7. So we can see that in the goal state, 7 is in the bottom middle. So it would take 1, 2, 3 changes to move that tile to its goal position. So here we would have a 3. So that means that whatever that first tile is, it is 3 distance away from its goal position. The next one we have 1. So that means if we go up here to the starting state, and the next one is 2, and we compare it to the goal state location here, we would only have to move it 1 block, so 1 distance away. So we add a 1 for that. We go to 4, and we can see that 4 is misplaced, and it would take 2 moves. They can move left and down, or down and left, and then it would be in the correct position as the goal state. So we add a distance of 2 here. And so what we do is go through each of these tiles and count the distance away they are from their goal location, and that gives us the overall heuristic value for the state. So here we end up with 18. So 18 would be the value, or the heuristic value of the starting state if we use this heuristic. One thing to note is that this heuristic is commonly referred to as the Manhattan distance. The Manhattan distance is like you can think of it as city block distance. So you can't move diagonal, you can only move up, down, left, or right. And so actually H2 is kind of like the sum of the Manhattan distances for each state. Okay, so another very common heuristic is Euclidean distance. And your book gives this example of of giving you this roadmap of different cities in Romania. So each one of these nodes is a different city, and then there's some step cost to move from city to city. And over here on the right, it gives you all of the straight line distances to a certain city. So in this case, it's Bucharest. I believe that's the goal that they're trying to reach. So each one of these numbers is the straight line distance to that city. And you'll notice that these values are going to be different than the step cost. So you might consider that if we want to move from one location to another location, maybe we have to follow roads, right? Like we follow all the roads to get there, and that is going to be a higher distance than a straight line distance. Straight line is always going to be less than trying to follow some roads that kind of zigzag your way there. So whenever we're trying to go through this graph that we've been provided to find the path to a certain city, we consider the step cost, or the edge cost on the graph. But then we also consider whatever that straight line distance is, because if we move to a city that has a smaller straight line distance to our goal, we would probably think, okay, that's going to get us to our goal faster. And so this is a very, very common heuristic that you'll see whenever you plan on any kind of like map-based problem. Okay, so how does this affect the way that we implement these algorithms? So one of the first things we have to do is edit our node class. So previously our node class only had values and parents. Now we have to maintain 3 different variables about the node. And the variables are generally titled G, H, and F. Those are pretty standard, so we're just going to call them G, H, and F. G is the path cost of the node, which you may recall the path cost is going to be the sum of all the step cost along the path, or like the path from the root node to the current node. H is going to be the heuristic cost of that node, so how close is this node to the goal node. F is just going to be G and H added together. Okay, and so we're not going to go through an example like we did last time with uninformed search, but I am going to show the slide that's kind of reminiscent of what we did with uninformed search and just talk about the ways that these informed search strategies change the overall algorithm. So one change we just went over, which is the node class, but then also within the set of commands, there are some differences. So the first one we're going to go over is greedy search, and greedy search is actually like a class of algorithms. There can be a lot of greedy search algorithms, and there's just any algorithms that only consider heuristic information. So with uninformed search, we were only considering path cost information. Greedy search, we're only considering heuristic cost information. So one of the things that changes here is that we don't maintain a closed list. So here we only maintain an open list, and whenever we pop off the open list, we're going to be doing that based on the lowest heuristic cost. An issue with not maintaining a closed list, though, is that it leads to infinite loop problems. So if you find some local minima, some node that it has a lower heuristic cost than any of its neighbors, but it's not the goal, then we're going to find that it's actually going to lead to infinite loop problems where we may go to one of its neighbors that is the lowest cost of its neighbors, then we add on the node we were just at, and it goes right back to it. And then we kind of like ping pong back and forth between these two nodes, and we never end up finding the goal. Another change we make is down here. Whenever we create the node object for C, we need to calculate the heuristic cost. This is going to be an explicit call, right? So we're going to have some function in our code that is like, titled heuristic, or maybe titled whatever that heuristic is. We have to call that and actually set the H field of the object before we add it to the open list. So this is something we didn't really have to do before because computing the path cost is actually pretty simple. But now when we incorporate heuristic information, we're going to have some call that is a little bit more involved. And for that, we're going to call some function that's going to compute the heuristic cost for our node before we add that node to the open list. And lastly, open list is going to be a priority queue based on the heuristic of the node. So that means that every time we come over here to node equals open list.pop, every time we call that, it's not going to necessarily pop off whatever we added on to the open list first or added on to the open list last. Instead, our open list is going to be a priority queue. So if you're not familiar with priority queues, what that means is that each item in the queue has some associated cost. In this case, our cost is the heuristic value. And every time you push something onto that priority queue, it's going to be sorted based on those costs. So the front of the priority queue is always going to have the lowest cost. So whenever we do openList.pop, it's taking whatever is at the front of that queue. But whenever we add things onto the queue, they're going to get sorted. So whatever's at the front of the queue is going to be the node that has the lowest heuristic cost. And in this way, it allows us to expand based on the heuristic information. So rather than expanding based on just the order that we push things onto the open list, with priority queues we can expand based on what's going to get us closest to the goal, or at least what we estimate is going to get us closest to the goal. So the time and space complexity of greedy search is big O b to the m, where m is the maximum depth of the search space, which you might recall is the same time complexity as depth first search. So you might think, well, okay, how is this any better? So actually the theoretical qualities of greedy search can change a little bit based on the problem and the heuristic that you choose. So in the very worst case scenario, the heuristic is going to do nothing for you, and you're just going to be doing like depth first search. But in the best case scenario, you're going to choose the node that's closest to the goal each time, and the reason you would do that is because your heuristic estimates that true cost pretty well. And whenever that happens, you end up expanding a pretty minimal number of nodes. So worst case scenario, it's b to the m, but actually, depending on our heuristic function, we can get pretty good performance. Last thing I want to talk about is just this local minima issue again. Whenever you use greedy search, you have to deal with local minima. So just to help you visualize what a local minima is, just in case you haven't encountered it before, if we have this graph right here, if we're on the bottom axis, horizontal axis, we just have all the nodes, and the vertical axis is the heuristic cost. We might get something like this, where as we continue through the state space, our heuristic gets lower and lower, and then it goes up again, and then down again. At some point, we're going to hit 0, right? That's going to be our goal. But we have all these like little dips, and so take this one right here, where at some point here, this curve is going to have a slope of 0, right? And at that place, it's going to be some node that has an h cost that's lower than all of its neighbors. And if we reach that point before we reach the goal, then we're going to run into problems, because we're just going to run into an infinite loop right here. So what that means is that you have to have some way of dealing with local minima. I noted that in the algorithmic part of it, they remove the closed list. But whenever we implement these things, we can still use a closed list. So even though, like, in theory, you're not, like, quote unquote supposed to have a closed list with a really kind of pure implementation of greedy search, I think that a closed list is a very simple and efficient way of dealing with local minima. And whenever we implement this in class, I think that's a very viable way of dealing with this problem. Okay, so the next algorithm that we're going to talk about is called A star. And so A star, you may have heard it before. It's used in a lot of different places, but it's an informed search algorithm that considers both the path and the heuristic cost when you select nodes for expansion. So recall that uninformed search strategies only use path cost. Greedy search algorithms only use heuristic. A star is going to use both. And so the way that it uses both is that the open list becomes a priority queue based on the F cost of the node. So you may recall a few slides ago we went over all these different fields to keep for your node class. G was the path cost, H was the heuristic cost, and F was G plus H. So whenever we push nodes and pop nodes off the open list, they're going to be sorted based on the F cost of the node, so the heuristic added to the path cost. So here, whenever we create node objects, we have to compute all of these things. So with greedy search, we only had to do the heuristic. With A star, we got to do a couple more things. We do the heuristic, the path, and the F cost. And then we just set all of those values, and then we add the node to the open list. So whenever we add nodes to the open list, again, because it's a priority queue, it's going to sort that whole list of nodes based on the smallest F cost. And then the kind of a big change from A star to the other algorithms is this if block right here. So for each child, previously we were just checking if they were in the open list or the closed list and then adding them to the open list. Now with A star, we're going to do something a bit more involved. Okay, so what this little block of code here is doing essentially is just trying to check if we reach a node that we've already been to before. Can we check to make sure that the path that we used to get to that node was actually the best path to get there? Or is our new path to this node better? So let's start with the easy case where it's in neither the open or the closed list. So we would check, okay, is it in the closed list or is it in the open list? No. Okay, come down here. If it's not in the closed list, then we go ahead and add it to the open list. No problem. But if we get up here and we find that this node is already in the open list, then what we're going to do is compare the G cost, or the path cost. So we're going to set new G equal to our current node's path cost, and then we're going to set old G equal to the existing node's path cost. So the existing node is the node that is already in the open list that has the same value as C. So then we're going to compare them. So if our new one is less than our old one, that means the new one is better. That means that the new node that we found, that for whatever reason we've already put in the open list, this new one has a smaller path cost, which means it's a better path through the state space. So what we're going to do is just remove that existing node and then add our new node. And then we'll check to see if it's in the closed list as well. If it was in the closed list, then we're going to remove that node from the closed list so that we do end up expanding it. And the reason we do this, again, is just to check that if we reach some node that is already in our open list, we just want to make sure that whatever path we use to get there is the best path to actually reach that node. There may be cases where we take a really roundabout way of reaching some node, and so it's going to have a really high path cost, but then there might be some other path through the state space that has a smaller path cost. And so this is how we account for that. We just compare the path cost of the nodes, and then if we find that our new one is better, we just replace what is in the open list with our new node. So keep in mind, we only consider the path cost when we're trying to compare them. We do not consider the heuristic cost. So the reason we don't consider the heuristic cost is because the heuristic cost does not depend on the path. The heuristic cost for a node is always going to be the same, regardless of how we got to that node. That's because the only input is some node and then the goal node. But for the path cost, that does depend on the path that we took to get there, because it's going to be the sum of all the step cost along the way. So whenever we do A star, we take this if statement that we had from before and we replace it with this fairly bigger if block. Okay, so one of the really nice qualities about A star is that it's optimal if the heuristic is admissible. So what we mean by admissible is that the heuristic cost never overestimates the true cost of the goal. So recall that our heuristic functions are just estimate values. They're just estimating what the true cost to the goal is, but they're not exact. So what that means is that some heuristics are going to be better than others. Some heuristics are going to underestimate the true cost. Some heuristics are going to overestimate the true cost. What you need to remember is that if your heuristic is admissible, then your result from A star is optimal. So the definition of admissible is that it never overestimates the true cost, so you need to remember that. Some people confuse overestimating and underestimating. It's like they kind of forget which one it is. So I have kind of a silly way of remembering it, but I'm going to share it here because it helps me. So imagine that you're throwing a ball to somebody. You're over here on the left, they're over here on the right, and the ball's in the middle. And this dotted line is like the trajectory that the ball takes, and the trajectory kind of represents like the heuristic function. So if you have a really good heuristic function, or you're really good at throwing a ball around, you can hit that person exactly where they want to catch the ball at. So you could throw the ball and it would get them right around the chest, and it's very easy for them to catch the ball and then return it back to you. Another option is that you underestimate how hard you need to throw the ball, and the ball ends up like hitting the ground in front of them and then rolling to them. It's not a very good throw. It's definitely not ideal, but this person on the right can still work with that, right? Like it's not going to go behind them. They can just reach down, grab the ball, and then they can easily throw it back to you. Where problems arise is that if you overestimate how hard you need to throw the ball. If you overestimate, then there's really nothing this person on the right can do, right? Because it's going to just go over their head, probably higher than they can jump and catch the ball, and then it's really pretty much impossible for them to be able to field that ball and throw it back to you. So this is the way I remember admissibility. If you get the heuristic right on the money, that's good. It'll still be optimal. If you underestimate the true cost to the goal, that's still admissible, and even though it's not ideal, your result is still going to be optimal. But if you overestimate the true cost to the goal, then this optimality goes away, and the result that you get from A star will no longer be optimal. Okay, so then this leads us to the question of how do we design admissible heuristics, right? Like how do we know that for each node that's in our state space, we're going to have a heuristic function that doesn't overestimate the cost to the goal for that node? So there is actually a strategy for doing this. In order to create an admissible heuristic function, all that you need to do is relax some constraint of the problem, or some like rule of the problem, and then create a cost based on that relaxed problem. So earlier we looked at the 8 puzzle problem, and one of the heuristics was the number of misplaced tiles. And so what we're doing is saying that we're going to relax the constraint of only being able to move stuff into the blank tile, and just say that, well, we could move any tile anywhere. And so when we do that, that's kind of like saying it only costs 1 to move any tile to its goal location. Even though we know that in the real problem it's going to cost more than 1 because we can only move stuff into the blank tile, and like we have this really weird kind of convoluted way of moving stuff around. But what we're going to say is, okay, let's just relax that issue. Let's just assume that we can move any one of these tiles anywhere we want. And whenever we do that, we end up with this heuristic function that just counts the number of misplaced tiles. And because we know that we've just relaxed a constraint of this problem and came up with a new cost function, you can kind of rest easy knowing that that heuristic function is going to be admissible, and it's going to lead to A star returning an optimal result. Okay, so let's look at the theoretical qualities of A star. So first of all, A star is complete. If there is a path to the goal, it's going to find it, or else it's going to return failure. It is usually optimal, so it's optimal when the heuristics are admissible. But since we have a strategy for that, we'll just say it's usually optimal. It's optimally efficient, which means that no other optimal algorithm is going to expand fewer nodes. The time complexity is a little bit different than what we've seen before. So it's big O, B raised to the epsilon D. So this epsilon value is going to be based on the heuristic function. So I put a little legend over here for this. H star is the true cost to the goal. H is the estimated cost to the goal, or the heuristic value. So here, what epsilon is computing is the relative error. So the better that your heuristic function is at estimating the true cost, the lower this value is going to be. And as this value gets lower, it's going to lower the value in the exponent, which is going to lower the overall time complexity. And the space complexity is the same thing. So what this is saying is that really the complexity values for A star are going to depend on how good your heuristic functions are, how well your heuristic functions actually estimate the true cost to the goal. So one thing to keep in mind is that for a greedy search, it says that the time complexity is B to the M, and I mentioned that the theoretical qualities could change based on the heuristic. This is kind of what I'm talking about. So in my opinion, the textbook just says B to the M, and they just say that it could change based on the heuristic function. I think what they should have done was something like this. So after kind of exposing this to the reader for A star, they should have went back to greedy search and said, really the time complexity for greedy search is going to be similar to this here, where we have some exponential formula that's true, but it's going to depend on the how well the heuristic estimates the cost to the goal. So your book has this really nice figure that compares the number of nodes that are expanded with A star in one of the uninformed search algorithms. And it's doing this over the 8 puzzle problem with different heuristic values. And so what you'll see, this is a iterative deepening search, which is like normally considered like the best uninformed search algorithm. But what you'll see is that when the depth is low, depth is only 2 or 4, IDS doesn't really expand that many nodes. But then as D rises, IDS starts to expand a massively huge number of nodes compared to A star. So when D equals 12, IDS is expanding what? This is thousands, so 3 million over 3.5 million nodes, whereas A star is only expanding 227 for one heuristic function, and then with a different heuristic function, they're only expanding 73. Then over here they compare the branching factor, which is like how many nodes are at each depth of the search tree, and you can see that IDS is going to be much higher than A star here. So I really like this figure because it really illustrates how much your results improve whenever you're doing informed search over uninformed search. And so just to recap, informed search algorithms take advantage of heuristic functions whenever they're trying to select nodes for expansion during the searching process. Heuristic functions are going to be based on the specific problem, so a heuristic function for one problem won't necessarily migrate over to another problem and work well. You may have to design them based on the problem that you're trying to solve. We looked at 2 algorithms, greedy search. Those only consider heuristic information, and A star search. A star considers both path and heuristic cost. And one important quality about A star is that it's optimal if the heuristic is admissible. And when we looked at the complexity values, both of these algorithms still had exponential time complexity, which is still very high, right? So theoretically, they weren't that much better than the uninformed search algorithms. But One, you gain optimality when you use A star in an admissible heuristic. And in practice, informed search is more efficient, right? So we looked at the slide, and the previous slide showed that table of how many nodes are expanded. And despite A star having exponential time complexity, it expanded far, far fewer nodes than uninformed search did. Okay, that's all. So just let me know if you have any questions. Thanks.